Okay, in the last video we reached to this equation. Now here I am splitting this equation. So on the left hand side we have L T inverse. It's proportional to, on the right hand side we have, I can write it as M L. This T is a power 2 in the denominator. If I bring it to the numerator, it is power minus 2 whole power A. And then we have M. L is in the denominator, so if I bring it to the numerator, we have a power minus 1 whole power B. Now here we have L T inverse whole power minus 1 is equal to, now I'll apply this power to all these quantities separately. So we have M power A, L power A, and T power minus 2A. And similarly here we have M power B and L power minus B. I can write it as, like, here we have length, time, here we have length, time, and mass. So mass is absent here. So here I will put mass also, so but I will put a power 0. So if I put this, then L T inverse. This is equal to the above equation, because anything with power 0 is equal to 1. So if we multiply this one by this one, we get again this equation, this factor. So if I multiply it by m power 0 or divided by m power 0, it doesn't matter, it doesn't affect our results. So we have this proportionality signs. So here we have this m power alpha A, and here we have this m power B, and they are in product, in multiplication. So we have this m power A plus B. So the power will 8 if two quantities are in the form of multiplication. Similarly, here we have the L power A, and here we have the L power minus B, and both are in multiplication. So we have L power A minus B, and we have this T left, which is a power minus 2A. Now comparing the power of mass M on both sides. So on the left hand side we have the power 0, which will be equal to, on the right hand side we have the power A plus B. This is, let's say, equation 1. Similarly, comparing the power of L. So on the left hand side we have the power 1. L is a power 1. On the right hand side we have the power A minus B. Here we have the power of L, which is 1. Here we have the power of L, which is A minus B. So we have to compare it, so they will equate it with each other. This is equation number 2. Similarly, comparing the power of let me check it, the power of T. So here we have the power minus 1, and here we have the power minus 2A, this is minus 2A, yes, because we have this power minus 2A. So here we have the power 2A, minus 2A. This is equation number. On the right hand side we have the power minus 1. On the left hand side we have the power minus 1. On the right hand side we have the power minus 2A. This is equation number 3. Okay, let me plug in the charge of my this one, because the charging is low. So Now from equation 3, from this equation we have 2a is equal to 1, because this minus 1 cancel with this minus 1. So a is equal to 1 over 2. Now using, I call it equation number 4. 4 and what we call it 1, let's say, we have a plus b is equal to 0. So a is 1 over 2 plus b is equal to 0. From this we get b is equal to minus 1 over a. B is equal to minus 1 over 2, sorry. So this is equation number 5, sorry. Now we have this equation. I call it equation A, let's suppose. This is the equation A. Now using equation 4 and 5 in equation A. Now using equation 4 and 5 in equation A, so we have equation A, which is v, speed of wave, which is proportional to t whole power A and mu whole power B. And we know that A is 1 over 2 and B is minus 1 over 2. So if we put it in above equation, V is equal to, V is proportional to t power 1 over 2 and mu power minus 1 over 2. We can write it as V is proportional to t power 1 over 2 over mu power 1 over 2. We can write it as V is proportional to square root of t over mu. If I remove this proportionality sign, we put a constant, which I replace it by c. The constant I call it c times square root of t over mu. But this constant c is equal to 1. So our speed of wave, which is proportional to the square root of t over mu. So from this equation we see that the speed of wave will be greater if the tension on the string is greater, and the speed of the wave is greater if the mass per unit length is smaller. So it means that if tension on the string, if the string is connected to two supports such that the tension here is on this way and here it is on this way. If this tension is greater, then the speed will be greater. And I already mentioned it before, that suppose we displace it from in mean position. If the tension is strong, then this string will move faster towards its equilibrium position. If tension is smaller, then this string will move slower towards its equilibrium position. So we prove it here. And the second thing was, like, I consider two string, one is thinner one and the other one is thicker one. If we pluck this string from its mean position, suppose this is the mean position, we pluck it, and similarly we pluck this thin string also from its mean position. And once we release, while keeping the tension constant on both this string we have the tension T here. Tension is same. Now if we release this plucked string, then this will move faster while this will move slower. So this is the dimensional analysis of what we call it, the speed of wave. And we also put this constant, which is a value equal to 1. And we can also calculate this constant value once we derive this relation by using the mechanical analysis. So here in my notes I wrote it like this, that this equation show that greater the tension in the string, greater will be the wave speed. In smaller the linear mass density, greater will be the wave speed. I wrote in my this notes that like this equation shows that greater the tension, in the string, greater will be wave speed, and smaller the linear mass density. Greater will be the wave speed, and vice versa. So this is all about what we call it the dimensional analysis. In the next video, I will draft same kind of equation, this equation, by using mechanical analysis, which I will do in the next video. Thank you.